Hey everyone, welcome to the video today. Today we're going to be looking at normal distributions. So in some of the other videos I've been talking about continuous random variables, and continuous random variables are variables that could have an infinite number of outcomes. So usually to do with measurement, with like numbers of measurements, it could be equal to anything, the answer to something. So it could be like heights of people or weights of something or other. And so any sort of measurement like that, distance that's traveled, in a year, whatever, they're all continuous random variables. Now, a particular continuous random variable, one of the particular distributions that we often talk about in maths is called a normal distribution. So often called a bell curve, the shape of that distribution. And the reason it's called normal is because it happens all the time in most things. And if you think about, like, just say heights, if you look at that red curve, if you think about the heights of people, most people are sort of in this area here, just looking at the red curve. Most people are of average height. And so you get most probabilities, the most results of that in that middle section. And then as people get taller, up here, there's not as many tall people, and so you see that red line coming down. The probability of being taller becomes less, and then as you get ridiculously tall up this end, then you get very, very few people up that top end. And same thing with short people here and extremely short people here. And so it just makes good logical sense that, yeah, of course, most people are in the middle, and the further you go each way, the less and less chance there is that someone is that tall. And so that's just a bit about normal curves. I think that makes sense to most people about how that works. And so just looking at, I've sort of just drawn three normal curves there, the red, the green, and the black. And there's only two parameters that we use to describe, I'm just going to do blue, a normal curve. Firstly, we look at the middle of the curve, so looking at that red line, and what we're doing in that blue, the green curve there. Sorry, my words aren't coming out right today. Is there, and the black line, black sort of. And so that middle part of the curve there, that is actually the mean, okay? So, that would be the mean of the red, that would be the mean of the black, and that would be the mean of the green curve, okay? So mu, the mean, is in the middle of the curve. The other measurement that we have for normal curves is also the standard deviation. And the standard deviation tells you about the width, about how sort of wide it is. And so you see how the red one, it's reasonably wide there, so like averagely wide. But you see how the green is actually a lot thinner, like it's a lot skinnier. It's all packed together. And the black one is like really wide. You sort of see how it sort of stretches out really, really wide. And so for the black, for the black one, black would have a large standard deviation. Okay, so on average, the values really deviate a long way from the mean. So black would have a large standard deviation, and green would have a small standard deviation. I hope that makes sense. A small standard deviation because all its values are tightly packed into here. Not the amount that they deviate from the mean is very small for most of them. And what you'll notice is that when you have a look at this, if you have a very small standard deviation, then actually the height of the distribution is a lot taller because you've got more values packed into this. There's more probability that someone, if it is heights, then someone will be in there. And you look at the black curve, that's actually a lot shorter because all the values are a lot more spread out. And what we're going to talk about is because these are actually PDF functions, they're actually probability density functions. That means that the area under these curves of all of them are equal to 1. And so that makes sense that if one's taller, then it would also be skinnier. And if it's not as tall, then it would be wider. And so that sort of actually makes sense with everything that we've learnt so far with probability density functions. So a normal curve, actually, it has an equation, and that's its equation right there, is that if just run over my example, so I'll be a little bit more careful going through here. And so if x is a normal distribution, then with mean mu and variance sigma squared, then the PDF is that function there. So f of x, I'm not going to read it out, but you can see it in front of you there. We write as x is a normal, so that means x is a normal, has a normal distribution with a mean of mu and a variance of sigma squared. And that's the function there. You notice that it's not a hybrid function, this one. That's because the function itself goes forever from negative infinity to positive infinity. There's no sort of, zero otherwise or anything like that with it. It's never equal to zero. In fact, it just stretches on forever and gets closer and closer to the axis. So there's your function. Let's just have a look at some very, very, very brief examples, and I'll answer this one in like 5 seconds. So if variable x, just looking at this example, has the PDF function there, write down its mean and variance. It's really easy to see that compare these two formulas here. So compare that formula with that formula there. It's easy to see what the standard deviation is. So here we go. So standard deviation, just looking at the formula, must be equal to 3. We can just read that off straight away. And we can see that the mu is equal to -2 because it's x minus mu, so it would be x minus -2 or x plus 2. The question did want the variance though, and not the standard deviation. So the variance is equal to 3 squared, which is equal to 9. Okay, and so that's the answer. Mu is 2, variance is 9. Mu is -2, and variance is 9. Hope that makes sense. You can sort of see how the mean and variance can be sort of employed into a PDF function. Now, you never ever have to use that formula because our calculators already have that function built into them whenever you do a normal distribution question, which you'll see in the next video. Very simple, but it's good just to know that formula so you know where it comes from. Okay. The only other thing I want to cover in this video is looking at sort of the what's commonly known as the 68, 95, 99.7% rule. And what it says is that if you have a normal distribution, then so if you start from the mean and then you go out to one standard deviation below the mean, and then up to one standard deviation above the mean. In other words, this area in here, I've drawn that pretty well, I'm happy with that. So that area in there, so if we are within one standard deviation of the mean, then that will equal 68% of the data. In other words, there's a probability of 68% that someone lies within one standard deviation of the mean. Hope that makes sense. 95, where does that come from? Well, if we stretch out to 2 standard deviations from the mean, then the rest of this area, so all that area, including the first lot of areas in there, so all of that yellow area is 95% in there. So if you add all those numbers up, you get 0.9. And again, what that means is the probability that a random variable is within 2 standard deviations of the mean, the probability of that is 95%. And similarly, if we go out one more standard deviation out to 3 standard deviations from the mean, if we look at that, then that will be 99.7%. And so almost all of the data comes within 3 standard deviations of the mean, and that is true for any normal curve. Now, these are approximate values. So if you're asked to find approximates, this rule is approximate. They're not exactly equal to 68%. It's pretty close to that, but I hope that sort of makes sense. So it's just good to remember that rule. If you get a question in exam 1 where you need to know an approximate without having to use a calculator, you can use the 68, 95, 99.7% rule. Okay, let's have a look at a question that you could get in exam 1, but this one's pretty easy, but just to give you an idea of what's happening here. So year 12 student heights are normally distributed with mu of 170 and standard deviation of 10. Okay, and so what I'll just sort of draw this just to make sure, because really the maths is not hard here, but I just want you to sort of make sure that you understand what's going on. And so the mu is 170. And standard deviation, I'll just do a different color line. Okay, and And so if we break up into sort of low boxes, and this will help us answer all the questions here, right? I'll just sort of get something going on. Okay, so standard deviation is 10, right? So then we can sort of go like that would be 180, 190. All these standard deviations are all 10 apart. 200, and then go down this way, it's 160, 150, 140, etc., etc. So I've gone plus or minus 3 standard deviations there. And I know that in there it's going to be, 68% there. I just put 60, oh, not 680, 68% from there to there, 95% from there to there, and 99.7% from there to there. Okay, so hopefully that sort of makes sense with what's going on here. So you can sort of 68% of Year 12 students are somewhere between 160 and 180 centimetres tall. 95% are between 150 and 190 centimetres tall, etc., etc. So hopefully that makes sense. Okay, so let's just answer these questions and then we're done with this video. So A, what's the probability that someone, I just said it, is between 160 and 180? So that's going to be 68%. We could also write that as 0.68, of course. Okay, done. Probability is there. Second one, probability x is greater than 160. And so this is a little bit tricky. I'm just going to rub off. I'll leave that there and I'll refer to the one up above. Okay. So that probability there, x is greater than 160. So just looking above, it's probably easier to see on this one here. 160 above, it's going to be this one, plus this one, plus this one, plus this one, plus that one there. Okay, so we're adding up all of those areas because it's minus 1 standard deviation, starting at 160, because that's 1 standard deviation under the mean. And so I've just got to add up all of those values there. And so if I just, I've got to do it with my calculator. Just get my calculator. So 0.34 plus 0.34 plus, I should have done that quite easily, but anyway, what have I got? 0.135, 0.135. Sorry, just totally mucked all this up. It's gonna, I haven't done that well at all. It's because I'm changing screens. I should really do something like this, shouldn't I? Much easier. So 1.35, here we go. I'm into 0.0235 plus 0.0015, give me a grand total of 0.84. There's an easier way I could have done that. I'll talk about that in a second. 0.84. Okay, so I'm just totaling up all of those. So it's 0.84. Also, you could write that as 84%. As we know, so 84% chance that that someone is taller than 160 centimeters. Okay, let's just do part C. Have a look at this. What's the probability that someone is less tall than 200 centimeters? So what we've got here really is we want this whole area under here up to 200. We want that whole area in there. And now we could total up all of those things. We could add up all of those things. So, adding up everything on that screen. And that would be, so, adding that to that, to that, to that, to that, to that, to that. No, I did that wrong. It shouldn't be including that first one. It would be that, plus that, plus that, plus that, plus that, plus that, plus that. That would give you the probability that we're after here. We could also just go 1, take away that one there. Because it's everything except for that bit there. And we'll just do that 1 take away 0.0015. Okay, so here it's going to be 1 take away 0.0015. Yeah, just making sure I got that right. And so what's that? 9. 0.9. See, this is testing me here. 9. And then 85. 0.9 and 85, which is the same as 99.85%. So I hope that makes sense. And so that's how we apply the 68 68, 95, 99.7% rule for as long as it's a normally distributed. Okay, so I hope that question makes sense. The numbers aren't always that easy, but that's just using those easy numbers just to demonstrate how everything works. Hope that makes sense. I'll see you in the next video.